and thank you for joining us on our presentation on our senior design project, the SOAR board, a solar-powered electric skateboard. This is our team with Franco Curcio, Julia Lampert, Antonia Jimenez, and Devin Jacobs. So previous skateboards usually have a simple design, and you have to push a lot, which is hard on your legs and balance, but they are convenient and they are sustainable due to the no carbon emissions. Our motivation behind wanting to do a solar-powered board is that it promotes transportation solutions that are sustainable and eco-friendly. It increases accessibility and affordability for e-boards. It's a versatile and enjoyable experience because you don't have to be an expert in order to ride it. And we will be able to use the same speed and convenience as regular e-boards. The benefits of our board compared to others is that it's power efficient, environmentally friendly. We don't use lithium-ion batteries like regular e-boards, which reduces the harmful chemicals and it increases our range with the solar power. It can be charged while riding due to the solar power. It's more accessible and affordable, and it's fun. Our goals are to create an electric skateboard powered solely by solar power. We want to make sure that the battery will charge with the solar cells. We can control the board with an app. We enable remote control operation as well as using our sensors on the board. And we want to do this with extensive battery life, high speeds, and safety, which will include LEDs in order to increase visibility and safety. This is our physical hardware block diagram. The colors show who bought what, but our work distribution will be explained later. For our engineering specifications, our highlighted ones are the ones that we find the most important and that we need to meet, so which are our solar cells, our motor and motor drivers, and our app connection to the board. The other four, which are the app controller, the rain sensor, the ultrasonic sensor, and the motor, are also very important, but the three that we have highlighted are the most important ones. This is our power flow chart. You can go ahead and take a look at it. So for our microcontroller technology comparisons, we went through 4 different kinds that we could have used, and we ended up choosing Arduino because we like C++, we like the Arduino IDE, and it's most important because it uses the 5V operating voltage due to our power block diagram, as you could see before. For our Arduino, we went with the Arduino Uno, not only because of its memory and RAM, but because of its strong community support, and as well as being able to connect a Bluetooth module to it. And here's a picture of our Arduino Uno.
When trying to figure out what the best battery was for our design, the first step was to figure out what battery type we were going to use. In order to do this, we created a comparison table between 3 different battery types: lithium-ion batteries, lithium iron phosphate batteries, and lead-acid batteries, and weighed them under 6 different categories: energy density, voltage range, cycle life, charging time, weight, and cost. In the end, we ended up going with the lithium iron phosphate battery types, mainly due to the fact that we were trying to stray away from lithium-ion batteries, as these were the norm for typical electric skateboards, and they were seen as quite dangerous in the community. And although these iron phosphate batteries are slightly more expensive, they have a very solid voltage range and high energy density, as well as a relatively low charging time as compared to the lead acid batteries. After narrowing down our battery type, we picked 3 different solid choices for our iron phosphate battery. These were the Meieri 2000 cycle 12 volt 6 amp hours battery, the Renogi lithium iron phosphate 12 volt battery, and the Expert Power 12 volt 12 amp hour battery. We rated these under capacity, voltage, energy density, weight, cycle life, charging time, and price categories. In the end, we ended up going with the Meieri 2000 cycle battery due to its low cost, its low charging time of 2 to 4 hours, its relatively high cycle life of 2000, its low weight, which is very important to the integrity of our design, and its high voltage output. The battery we ended up going with was the Meieri lithium iron phosphate rechargeable battery, with a maximum voltage output of 12.8 volts, maximum current output of 6 amp hours, and a power rating of about 76.8 watt hours. The physical dimensions are listed here at 3.54 by 2.75 by 4.33 inches, with a weight of roughly 1.65 pounds. Taking a look at the different types of solar cells that are commonly used for projects, these included the monocrystalline solar cells, the polycrystalline solar cells, and the thin film solar cells. We rated these under 4 categories: efficiency, size, cost, and a variety of keynotes. In the end, we ended up going with the polycrystalline solar cell types due to the fact that they were relatively small, although the same as monocrystalline, but a little bit more durable than the monocrystallines. And we found that these were a little bit more widely available in the market as opposed to the monocrystalline counterpart. Although we lose a little bit of efficiency, we gain the option to attach more solar cells in the event that we find that they are not suitable. When it came down to pick an exact solar cell product, we weighed 3 different options: the Sonyema 10-piece polycrystalline solar panels, the EcoPower 12-watt polycrystalline solar panels, and the AllPower 10-watt polycrystalline solar panels. We ranked all of these under efficiency, size, voltage, current, power output, price, and key features. In the end, we ended up going with the Sonyema 10-piece mini polycrystalline solar panels due to the fact that it's much cheaper and much more compact than the other 2 options. And these have a much higher efficiency rating than the 2. And although they may have a lower power output and lower voltage output, the fact that they're cheaper allows us to purchase more and put them in series and output much higher power than the previous 2. As stated previously, these solar cells are made for polycrystalline material, which makes them less expensive, more durable, and more reliable. They're also fairly small, which allows us to maximize the amount we can put on the surface area of the board. These hold a voltage maximum of 5 volts and allow for a higher amount of current to flow through it, enabling a higher power output and increasing energy production. Most importantly, they are also environmentally friendly. So as we see here, these are the solar cells that we have selected. Going over the specifications once again, they output a current of 60 milliamps, a working voltage of 5 volts, and their dimensions are 2.67 inches by 1.45. And once again, they are polycrystalline panels. Transitioning over to the motor comparisons. To pick our motor, we had to first pick the type of DC motor we were going to use. These included brushed DC motors, brushless DC motors, and series DC motors. Each of these were compared under design, application, efficiency, speed control, and cost. In the end, we ended up going with a brushed DC motor due to the fact that it has a relatively high efficiency rating, although slightly lower than the other 2, but it also has the ability to control speed using voltage regulation, which for us seemed like a simpler option as opposed to more complex ESC methods. In addition to this, a brushed DC motor proved to be much more cost effective in the end. Once we concluded that we needed a brushed DC motor for our design, we looked at 4 different motors and compared them individually to see which one was most suitable for our design. We looked at the 775 motor, the RS550 motor, the 540 motor, and the 360 motor, and weighed them under the categories of kV rating, max output power, weight, noise output, efficiency, and price. In the end, we ended up going with the 775 motor, which, although it was priced at slightly higher than the other 3, it had the highest kV rating out of the 4, with a max kV rating of 20,000 RPMs per volt. This is very important to our design as we want to have the most torque possible on our board to allow it to move as quickly and as effectively as possible. Taking a closer look at the motor we selected, the 775 motor, we see here listed the specifications of the motor itself. Starting with the voltage needed, this motor requires a input voltage of roughly 12 volts to operate. It also has a motor diameter of 42 millimeters, a motor length of 66.5 millimeters, and a weight of 200 grams. This means it's fairly portable and lightweight, allowing it to fit perfectly with our design on the board and reduce weight on the board. Once we had our motor, the next step was to have a motor driver to be able to control the speed and direction of the motor preferably. To do this, we had to decide what type of motor driver technology we would be using. We weighed 3 different options against 5 different categories, being integrated motor driver, H-bridge motor driver, and stepper motor driver against design, control method, efficiency, cost, and applications. In the end, we ended up going with an H-bridge motor driver because of the fact that this allows us to control the exact direction and speed of the DC motors, allowing for bidirectional control and speed control through the use of pulse width modulation. Although it has a slightly lower efficiency, it comes at a lower cost, which saves us a lot more money and increases precision. When narrowing down our motor controllers, we had three different options: the L298N motor driver, the high LEGO BTS7960 controller, and the TB6612FNG dual H-bridge motor driver. We ranked all of these under voltage range, maximum current, motor channels, control interface, and price. In the end, we ended up going with the BTS7960 as labeled in the chart. This is due to the fact that although it has slightly lower voltage rates than the L298, it gives us far more control under the ability to use pulse width modulation, direction control, and current limitation, allowing us to have a safe circuit throughout our system, and it gives us a maximum input current of up to 48 amps, which gives us more freedom when designing our circuit.
For the motor drive controller board, we chose the BTS 7960. The reason we chose this board is because it pairs well with the Arduino. It operates at a voltage of 3.3 to 5 volts, which works very well. This board will be responsible for interfacing with the microcontroller, and the Arduino will be responsible for driving and controlling our motor. This board should work very well within our design. We have introduced a MPPT solar controller into our design. The inclusion of this solar controller was necessary to ensure that the battery gets a sufficient amount of charge without being overcharged. It'll be able to adjust the voltage that the battery is receiving, and it ensures the optimal amount of power will be sent to the battery and is an overall safety and longevity measure included into the design. The solar charger comparisons, we have the MPPT solar controller titanium battery charger module, the MPPT solar panel controller, and the waterproof PWM solar charge controller. The input voltage 12 to 28, 8 to 28, with an output of 5 to 26 for the MPPT solar controller. The MPPT solar controller is the one that we've decided to use as it works well for our design. The MPPT solar controller, solar charger, works well for our design because of how well it pairs with the Arduino, which is a key element of our design. The input voltage has a good range, which should fit in with the range of input that we would be expecting, and output voltage also matches up with what we want in our output. So overall, this was a good solar charger that works with our design. For the LED comparison, we have three sets of LEDs: the BTF lighting WS2812B, the BTF lighting WS2812B, 100 pieces individually accessible RGB LED pixel. We have that with 100 pieces and a strip, with the others compared to 144 pieces and 300 pieces. The 100 pieces is overall the lowest cost, is compatible with our Arduino, has a DC input voltage of 5 volts, and will be controllable through the app, which is why it was chosen. Here we can see the BTF lighting WS2812B and the reasons why it was chosen. Notably that it was the lowest one in price. 100 pieces of LEDs should be sufficient for our board. 5 voltage DC input is good for what we intended for. It is cuttable and we will be able to control it through the app, which is ideal for our design with the Arduino and its Bluetooth capabilities. For the deck, we have a longboard deck, which is made out of bamboo, which is a good material because of how lightweight it is. Longboard deck is good because it gives us more surface area to place more components, more solar cells. It comes in at a length of 38.75 inches and a width of 9.65 inches. We do have to make some modifications to this board. We've cut an indent to place the solar cells into this board. We'll also be drilling a hole to connect the solar cells. Here is a look into our PCB where you can see such components such as the microcontroller, the Arduino Uno, a step regulator, our solar cells, various sensors, headers, and pin connectors, all combined together to make the design for the solar board. This is an image of the earlier schematic design transformed into a board which will be sent into a manufacturer, which will be made and then sent to us. An insight into some of the challenges that we have faced in the hardware section of this project. We originally bought a motor for this project, but through testing we learned that it was not compatible with our design, so we had to buy a new one. We bought a battery with a 12 volts, but we figured out that we needed more than 12 volts. We needed 24 volts for our design, so we did buy a second 12 volt battery to achieve the required voltage. The deck that we bought did not come with space for the solar cells, so we did make the indent in order to have a place to put the solar cells. The solar cells, when we got them, did not come with wires, so we soldered wires onto the cells in order to connect them to each other and to the system as a whole.
Now, it is important to understand how the board and the app will work, what things they will do, and how they will interact with each other. From the MCU, we will be getting the battery and the speed information, and from the app, we will be controlling with the help of the MCU the increase and decrease of speed, as well as setting a cruise speed and the LED light customization feature. In order to set up communication between the board and the user, we first thought about developing a controller made up of 3D parts and a circuit to operate it. But since our project's goal is sustainability and being eco-friendly, we thought developing an app would also be a great idea. This statistic gave the app the win since we can see that the users with smartphones have been increasing over the past few years, aligning with our goal and making our solution a differentiator. For the app testing, we wanted to start by testing, since the early stages, the communication within the board and the app. And this can be done with these two apps, MIT App Inventor and Codular. Both of them are free and coding free. We end up choosing MIT App Inventor since it is easy to use. It will help us test if we're able to control the app, the motors, and also we can develop for both App Store and Android, which Codular can just develop for Android. Once we know that the wireless communication is working fine, we will move on to our second development phase, where we will be using Expo and React Native. Expo is great for development. It has over-the-air updates, no need to link a lot of libraries to develop, and has already some pre-configured tools. The most amazing feature is the mobile UI part, which aligns with over-the-air updates. React Native, on the other hand, will enable us to set up wireless communication using Bluetooth and can be developed for both iOS and Android. Since both of them are compatible, we have chosen to use these two frameworks to build our app. At first, we choose to work with Expo since it is easier to use and has a lot of advantages in comparison to React Native. But after knowing that Expo does not handle the feature to work with Bluetooth, we have decided to use React Native. The process will consist of developing the whole app on Expo and ejecting the project to React Native to add the Bluetooth wireless communication. Here's the first design we developed for our app using Figma. As showed before, these are some of the features that the app will have. It will have the ability to connect to the board, control the speed, and the LED light setup, as well as turn on and off the board. The information such as the battery and the speed at which the board is traveling in real time will be displayed. This is the software flowchart and the logic we used to make this development user-friendly. At first, the user will be prompted to the home page where the on and off feature and the LED lights setup as well as the Bluetooth setup will be displayed. Once the board is on and connected, it will be directed to the landing page where the app will display the battery and speed information as well as give the ability to control the speed to the user. The flowchart ends with the user turning off the board after it has been used to recharge and save some energy. Here are some of the challenges we have been facing on the software side. At first, when we knew that Expo did not have a Bluetooth connection, we went ahead and researched for a framework that could give us that accessibility as well as be compatible with the Expo project that would be ejected. The second one is that uploading an app to the App Store is really expensive just for one time, so we're still deciding if we will be using just the Android App Store or also the App Store. Later on, there is no knowledge on how to use Expo or React Native, so it is creating a big learning curve for the team. And finally, we have no experience with wireless communication before, but we are positive that MIT App Inventor will help us bridge this gap.
Here we have our progress bar chart where we have about 50% done with our Arduino code, about 30% done with our app development, or almost 100% done with our board. We have a prototype that's about 70% done. Our major components have all been demoed. Our PCB design is almost completely done, and we have acquired all of our parts. For our work distribution, you can see here that not everybody works on everything, but we all will be working together in order to have a good team communication, and we all have our own certain components that we like to work on, but we do all come together to work on everything. For our finance and budget, we have our estimated cost for everything and the actual cost of things. And the estimated cost total, it's a little bit lower than our total cost, but that's because everything is only as like one product. So in our actual cost, for example, solar cells, we've bought 30 solar cells for $66 instead of 10 for $20, as you can see. Thank you. Let us know if you have any